Hello everyone, let's solve the problem minimum distance between BST nodes. Let's read the statement. Given the root of a binary search tree, return the minimum difference between the values of any two nodes in the tree. What do we mean by that? We are given a binary search tree and we are supposed to return the minimum difference between each and every pair of nodes that is present in this tree. See, this is our tree. Let's take a pair 4 and 6. The difference, absolute difference is 2. We are taking the absolute difference, the distance, okay, that is 2. 6 minus 2 is 4. 4 minus 2 is 2. 3 minus 2 is 1. 2 minus 1 is 1. So out of all of these, 1 is the minimum, right? So this is our answer. Now, how are we going to do this? Let's think of a brute force way. We need all the pairs, right? So why not try and make each and every pair? So 4 and 6, 2 and 6, 4 and 2, 1 and 2, 3 and 2, 2 and 1, right? But if we do this, we are going to consume a lot of time. If we have n nodes in our tree, we will have total n square pairs. Okay, so that would be very inefficient. How do we make it efficient? How can we not do this and do some better way? For that, we will have to look into the property of a BST. The basic property of a BST is the in-order traversal of a BST gives us a sorted sequence. Okay, what will be the in-order traversal of this binary search tree? It will be 1, 2, 3, 4, 6. It is sorted. Now, what is exactly in order? The in-order traversal is left node or left subtree, process current, that can be anything, that can be adding or anything, then write. So we are at 4. We will go to left. As long as we are able to go to left, we will go to left and add this, because after that we have nothing. Then we will come back and process our current node, that is 2. Then we will go to 2's right, that is 3. This subtree is done. Now this subtree is the left subtree of which node? That is 4. Now we will process 4, that is add. It's done. Now we will go to the right of our current node. Now we have only 6. So this is what an in-order traversal is. This is actually out of the scope of this explanation, but still I thought it's better to tell. Now we have the sorted sequence, right? How can we get the minimum difference out of these? We will take the difference of each pair. Why each adjacent pair? I mean, why each adjacent pair? See, difference of 2 and 1 is 1. 3 and 2 is 1 again. 4 and 3 is 1. 6 and 4 is 2. See, we are getting the minimum differences, right? Why adjacent? Because if the difference of 1 and 2 is 1, and instead of 2, if we take a greater number than 2, then the difference is definitely going to be greater than 1, isn't it? If we have 1 and 2, the difference is 1. Instead of 2, if we take 3, the difference is definitely going to be bigger. If we are at 3 and instead of taking 4, let's say we take 6, so the difference between 3 and 6 is definitely going to be bigger than 3 and 4, right? So that's why we are taking the adjacent values. So the minimum difference is 1. So what we are going to do? We are going to perform an in-order traversal, and after that, doing that, we will get this sequence, right? And then we are going to take the difference of adjacent values, and we will keep a record of whichever is the minimum difference, and then we are going to return the minimum. This approach will have a time complexity of big O of n to traverse all the nodes, and another n to traverse this sorted sequence, because we will take the difference at each step, right, which is nothing but O of n, and the space complexity will be, this is the time, the space complexity will be O of n, because we are storing the sequence, right, and h. What is h? H is the recursive stack space, right, that is the height of the binary tree. Fine. Now can we do better than this? Yes, definitely. We are doing an inorder traversal, right, and the inorder traversal is giving us a sorted sequence. In other words, we can say that if the inorder traversal is giving us a sorted sequence, that means the inorder traversal is moving in a sorted fashion as well, right? That's the reason we are getting a sorted sequence, right? So can we use that idea and get rid of our this space, this extra n space? Yes, we can. How are we going to do this? Let's see. We call our inorder from here, right? Now what our inorder will do? It will go to the very bottom at the left, isn't it? It will reach here, right? Then it will start computation from here. We will initially keep a previous dummy tree node that will be initially null, and at global we will keep a difference. Okay, we'll keep a difference. We will have a previous node, we will have a current node, right? Okay, now we are here. Okay, it sees we have nothing on both sides, isn't it? So it will come back here. Now we are currently at 2, but before coming to 2 we will set this one as our previous. Okay, we'll set this one as our previous. Now what is the difference between previous and current? It's 1. Now we'll go to 3, we'll go to our right side. Now our current is 3. What is the previous? Previous of 3 is 2. What is the difference? It's 1. Now this, we are done looking at this subtree, right? Now we will directly move from here to here. That's how inorder works, isn't it? So our current is now 4. For 4, what is the previous? It's 3. Now what is the difference? It's 1. Now we are done looking at this. Now we will go to this. So our current is now 6. For 6, what was the previous? It was 4. What is the difference? It's 2. It will go here, it has nothing, it will move back. It will go here, nothing, go back, go back, go back. So this is the differences that we have got. And what is the minimum? 1 is the minimum, right? So we will return 1. Now let's quickly code this. We will need a difference, right? Minimum difference. Let's say min diff. It will initially be max value. We will need a dummy node. Say previous equals to null. Now let's quickly write our inorder function. It will take the root. If our node is null, we can't do anything, return from here. Otherwise, go to left. What was the inorder traversal? Go to left, then process the current node, right? Then go to right. Now let's call our inorder, and at the end we will return our minimum difference that we have achieved. Now what are we going to do here? We will first check, do we have a previous node? If it's not null, means we have a previous node. We will take the difference of the current and the previous. Say math.absolute previous.val minus root.val. Now what is minimum difference? It is the minimum of the minimum difference so far and the current difference that we got just now. Done. Now what we will do, we'll move to our next node, right? But before doing that, if we move to our next node, our current node will become the previous node of that next node, right? So we will set previous to current. Then we will go to right. Let's see if this works. Definitely. Nice. Now let's do a dry run. Our previous would be initially null. We will have a current. Different would be initially max, right? Okay. We begin from here. We go to 4's left. Okay. We go to 2's left. Okay. We go to 1's left. We have null. We roll back. Now we come to this line. Now, do we have a previous? No, right? So let's set our previous to current. Our previous now becomes current, right? It becomes 1. Then we go to right. We have nothing. All right. So for 2, this area looking at the left is done. So after we return, we will directly go back here, right? Okay. Now what is the current node? It's 2, right? We will see. What is the previous? It's 1, right? What is the difference? It's 1. Okay. Now what will we do? We will set our previous to our current node. That is 2. Now we will go to right. We'll go to right. Fine. We come here. We go to for 3. We go to left. Right. We have nothing. We come back for 3. We come to this new line. We see. Do we have a previous? Yes. What is the previous? It's 2. Right. What is the current? It's 3. Obviously. Let's take the difference. The difference is 1. Fine. Now let's set the previous as the current node. So our previous becomes 3, isn't it? We call in order for our right. Okay, we have nothing. Okay, we'll roll back. We'll roll back to where? We'll roll back to 4. That's how the order works, isn't it? We were this whole thing was running for the left subtree of 4. So after it's done, we'll come back to here, isn't it? All right, fine. So what is the current now? It's 4. What is the difference? Difference is 1, right? Now let's set the previous to the current. Previous was 4. We'll now move to right of 4, isn't it? For 6, we are at 6. We'll move to the left of 6. We have nothing. All right, come back here. What is the previous? It's 4. What is the current? We are at 6. So the current is 6. What is the difference? The difference is 2. Fine. Let's set the previous as the current. Set the previous as current. Okay, we'll go to right. We go to right. Do we have anything? No, we don't have anything. We roll back. Roll back to where? Totally out, because this was the left subtree for 4, right? The main call, the initial beginning call for our in order. So we are totally out of the thing. Our minimum would be the minimum would be this. We will have a minimum difference globally. Okay, and we will return this. So that's how the in order is working here. We didn't use any extra space, so space complexity becomes O of h only. That n that we had initially is now gone, right? The time complexity is O of n. We reduced the time complexity of O of twice of n to O of n because we are not doing a for loop on this sorted sequence, right? See, it was O of double n, isn't it? So this is our solution. We can perform a BFS as well, the iterative way, but that would be a matter of extra space again, right? Because we will have to use a queue. So this is the most optimal solution. All right. So yeah, if you like this video, hit the like button, share this to your friends, and definitely subscribe, and I'll see you in the next video. Bye bye.